Hello, today I'd like to give more bits on signed and unsigned integers. Let's think about 8-bit integers and let's think of them progressing in an unsigned sequence. So we're going to be looking from a decimal perspective, taking the integers from 0, 1, 2, we're going to skip to 127, 128, 129, and we're going to skip to 254. And then finish at 255. So that's how many integers we would have if they were unsigned, and I'm presenting these here in decimal form. So you have the 10 to the 0 place, 10 to the 1, 10 to the 2. So that's decimal. The binary equivalent over here, we're going to show that as 0b with the 8 bits. So here your bits are going to your bits are going to be either 0 or 1 because it's binary, and you're going to have the 0 place. It's going to be, the ones place is going to be 2 to the 0, 2 to the 1 is going to be your 2's place, 2 to the 2, it's going to be your 4's place, 2 to the 3, your 8, 16, 32, 64, 128. So those are the places in the binary system. And then you can see the progression where you start with all zeros, and then you go to 1, you go to 2, and then you jump all the way up to what would be 127. So that would be 64 plus 32 plus 16, etc. And then if you were to take this and add 1, then that would put a 1 in the 128 place, and it would zero out the lower bits. So that's where you go from 127 to 128. You continue with adding a 1, and that would be 129, and then you jump all the way to 254, and that would be all ones except the last place, and then you finish up with going to all ones. If we think about hexadecimal equivalent, these are really synonymous because you can think of the lower nibble, the lower 4 bits of the byte. It's called a nibble. You can think of that as the ones place in the hexadecimal format. So it makes it nice as a one-to-one correspondence between what you have on this side and what you have here. Just collecting the bits together. So here, that's a 2. Here, these 4 bits would be an F or foxtrot. And these upper 4 bits, these upper 4 bits or the upper nibble would be a 7 in this case. And then you transition to an 8-0, an 8-1 foxtrot, and then you have an echo. So here your digits in a hex format, you have 0 to 9, but then you have to add in the higher values of A, B, C, D, E, F, which would be 10, 11, 12, 13, 14, 15. And that takes care of the hexa equivalent. If we think of the integers arranged in a signed sequence, then you're going to be looking at the same thing for 0, 1, 2, up to 27. But that sort of starts in the middle of the range for signed. And then if I were to do a thought experiment, say, okay, if I had a -1 integer and I were to add a 1 to it, yeah, I would get 0. And then I think about, well, what binary value could I have that would give me that capability? So if I had all ones and I added 1 to it, yeah, I would get all zeros here, and I would have, if I had an 8th binary place, that binary place would see that 1, and that may be thought of as a carry bit or something like that. But in any event, this would be the equivalent of -1, such that if I were to add 1 to it, I would get all 0 bits. And then just taking that thought process even further backwards, foxtrot echo, if I were to add 1 to that, that's my -2. If I add 1 to that, yeah, I do get -1. And then I just keep working backwards until I get to the very beginning of the signed sequence, which is going to be hex 80, or the 1 there with all zeros, and then I start adding 1 to it. If I had that as -128 and I add 1 to it, yeah, I do get a 1 there and an 81. So that's how the signed sequence works, with 0 sort of in the middle of it. You could do a thought experiment here and just ponder about, well, what if I had a 3, a row corresponding with 3? So I would have a 3 here, I'd have a hex 3, and then this would be a 1, 1. So that's what a third row would look like. And the complement of that, the -3, would have here would be a foxtrot, a delta D, and so a D would be a 1 here, and then a 0, 1. That's what that would look like. But this seventh place here in the sign sequence, that is your sign bit. From time to time, when dealing with binary data, you hear this term 2's complement, and I wanted to discuss what that is. The 2's complement of an integer x, it ends up being really -x. It just negates it. So say we were using signed 8-bit, just like we were just a moment ago, and even the integer 3 that we had as a thought example earlier, so that's going to be hex 3. The binary representation of hex 3 is going to be all upper zeros with the lower 2 bits being 1. So that's a binary 3. So there's a thing called a 1's complement, and that is just a bitwise complement. So what you do is you take each 0 and replace it with a 1, and then you take each 1 and replace it with a 0. So that's what the 1's complement would look like for a 3. And then the 2's complement is just taking that result and adding 1 to it. So you end up taking this and adding 1, so that puts you back at that foxtrot delta that we had before, and that is -3. So that is what a 2's complement is. 2's complement is just you take the binary complement and add 1 to it. Next, I want to talk about bitwise functions. And I realized that you may never have seen this before, and I want to show both the C language and the MATLAB equivalent. MATLAB looks a little bit cumbersome, so I'll just use the C language versions in the discussion. But what you do is you have an AND bitwise function, you have an OR, an exclusive OR, you have that 1's complement I referred to earlier, and then you have some bit shifting. Either you bit shift to the left or you bit shift to the right. And this is how you show in C, what it looks like in C. And here's how you show the same thing in MATLAB. So let's take some examples here, bitwise AND. So let's say that we have A given as this and B given as this, and we want to know, well, what is A and B? And really, you just go bitwise. You say, okay, 1 and 0 is a 0. 0 and 1 is a 0. 1 and 1 is a 1. 1 and 0 is a 0. And then, of course, these all are 0, 0, so they're going to be zeroed. So this is the result. And what you can think of, I use this for masking. And let's say that B is a mask. Mask is B, and then you kind of want to know, well, what bits of A are on, quote unquote on. And if this were my mask, then I could tell, well, the result showing that 0, 1, the 2's place, or I'm sorry, the 4's place is on. So that's what the AND function looks like. The OR function looks like this. I'm going to keep A and B the same. So since I have 1's in the lower nibble, if I'm looking at A or B, I've got 1 is going to be on if I think about an OR perspective. in all 4 locations, and then I have no bits on in either A or B for the upper 4 bits. So that's what the OR looks like. Just taking the OR of each bit location. Exclusive OR, what that means is if you do have a 1 and a 1 in both A and B, then that goes to a 0. So it's exclusively ORed, so it has to be a bit to be a 1 here. You need a 1 in A or B, but not both, I guess might be a way of thinking of it. And then the 1's complement. For the 1's complement, again, you just take every position and you just do the complement of it. So 0 is replaced with a 1 and a 1's replaced with a 0. And then here's a bit shift to the left, and I've just taken as an example, we're going to do it two places. So if I start with A like this, then I'm going to fill in zeros there, and I'm going to take that, what looks like a D, and shift it to the left two bits. So I kind of lose the upper 2 over here. This is the equivalent of multiplying by 2 to the k, or in this case 4. Okay, let's check that. Well, this is D. If I take D, which is 13, and multiply by 4, in this case, 4 times 13 is 52. Let's see what this is. Well, I've got, that's the 16's place, that's the 32, so that's 48. 48 plus 4, yea, verily, is 52. And then I'm going to look at bit shifts to the right. For this one, when you're looking at MATLAB, you use the same function. It's just that if you're shifting to the right, you're going to have a negative k over here. But thinking of it in terms of C here, I'm going to use k's too, and I'm going to shift to the right. And for this situation, when you shift to the right, I'm going to be adding zeros on the upper end, and I'm going to end up with these 2 being in the lower bit positions, and I'm going to lose the 0, 1. And this ends up looking like that you're dividing by 4, in this case, 2 to the 2. So if I had 13 and I divide by 4, yeah, I guess I do get 3. So that looks right. Okay, sign extension. So we're shifting to the right. So there's a question of, well, what bits go there? And this particular example is good for signed or unsigned, so we don't have to worry about sign extension here. But if I had this situation where I have Foxtrot or an FD, and I think of this as unsigned, it's an unsigned 253, and I take an unsigned 253 and I divide by 4, I'm going to get, the result is 63. And this is correct. So this would be an unsigned situation where the bit that comes in here is a 0 to give me the correct answer. The extended bits are 0 for a unsigned integer. But if it were signed, like I'm going to take this again as FD, and I'm going to say it's assigned -3, and then I divide by 4, well, the result should be -1, and I've got to have that bit that comes in as a 1. So the extended bits are 1s if it's a signed scenario. So that's a little bit of a gotcha there for the bit shifts to the right. There is an ASCII table that maps characters to unsigned 8-bit values. So characters like 0 through 9, exclamation, quote, dollar, etc., even the capital letters A through Z, the alphabet, the lowercase letters A through Z. And how this mapping looks like, the hex value of A, for example, is 41 hex. So you see the row 4, and then you see the column 1. That's how it works. And then decimal wise, it has 64. A would actually be 65. B would be 42 hex or 66. C would be 43 hex or 67. D would be 44 hex or 68. So that's how it works, mapping text into 8-bit unsigned. The notion of binary data can be extended to 16-bit very naturally. You just, from a decimal perspective, you have to add additional digits on the high end. And then for hex, for 16-bit, you would add 2 more hex digits. And then binary-wise, you would add 8 additional digits. Signed bit, again, becomes the high bit of the system. And the way I've presented this particular sequence is in an unsigned sense. I wanted to talk about a few more things on integer. Infinitely accurate for addition and multiplication. That's true as long as you don't overflow. Like if you have an 8-bit signed 127 and you add 1, you're going to roll that over. So that's a concern. Division is not accurate. You end up truncating. For example, we talked about 13 being divided by 4, and then we ended up with a 3. So that was a little bit quirky. We lost some data there. So that's for integer. So addition multiplication is good with those caveats. Indianness. So that's with an E. So I wanted to talk a little bit about that and how I present that is I think of data as a sequence of 8-bit characters or bytes. And as an example, I'm going to give you 41 hex, 42, 43, 44, and then I'm going to follow that up with a couple of zeros. So we've got 6 bytes of data, and we're going to look at that in a number of different ways. If we look at it as ASCII data, then that would be the A, B, C, D that we had earlier from the ASCII table. And if we were to think of this, on the other hand, as 16-bit data, and we think of it as little endian, what that means is that the lower byte comes first. And really to consider this as 16-bit data, you'd have to turn the bytes around and put 42 in front of 41 as a higher. And then here 44 would be the higher byte for the 43. So that's little endian. On the other hand, if we were going to call this big endian order, then the high byte would come first, and you go ahead and write 41, 42, and then 43, 44, followed up in either case by the zeros. So that's the way data can be viewed. Another thing to kind of watch out for is alignment. Like if we needed word 16-bit alignment, then sometimes things get padded with additional zeros so that data starts on 16-bit boundaries or 4-byte, 32-bit boundaries. So alignment can sometimes get you. 2's complement, we did discuss that. And as far as the fixed point sense, we can show a Velodyne example now. So Velodyne, that's the puck that I have here in this view, and that puck is going to be looking down at the ground. That's what this particular project was. So we were looking at the ground and trying to figure out some things from that. So this is a LiDAR, the Velodyne LiDAR. And this is a good example of unsigned. I'll show you now. Here's the data sheet for the Velodyne LiDAR. It's a 16-beam LiDAR. And when I go and take a look at the sensor definition, here's what we're looking at. You have omega showing the different beams that are swept around. And then what happens is the beams are swept by an azimuth alpha. And really the key thing here is in a spherical system is the range to target, and that's the capital R that we're going to be interested in. Here we're looking at some raw data coming from the Velodyne. This is an example of a particular laser beam at a particular azimuth. This is a particular range to target here. And the data looks like an an 89 hex followed by a 59. So what they say is it's little endian, so you're turning the bytes around. So it's going to look like a 5989 hex, and then when you convert that to decimal, you get 22,921. So what this means is with the 2 millimeter resolution, when you take 2 millimeters and multiply it by 22,921, that gives you 45,000 millimeters or 45.842 meters. So that is from a fixed point perspective, that's what the data means. Another good unsigned example is the analog read that you have in the Arduino. Like if you hook up a sensor that is looking at 0 to 5 volts coming in, well, that 0 to 5 volts corresponds to a 0 to 1023, and that amounts to a 10-bit resolution, and you get, if you have 5 volts divided by 1024, you get 0.0049 volts per unit. So that's another good example. The Arduino was a 10-bit unipolar analog to digital converter. Here I'm going to show you a 16-bit analog to digital converter. It's about the size of a half of your pinky nail, very small chip. You could actually hook this up to an Arduino and talk to it. But anyway, this particular one is unipolar or bipolar. Here's an overhead view of the pinout of the chip, and the Arduino would probably talk to it using some of these pins. You would give power to the chip using these pins and this pin and the analog grounds. And if it were a unipolar, you maybe go 0 to 10 volts. And this tells you how to connect to R1 in and R2 in, that kind of thing. And then that's unipolar. And then bipolar would be plus or minus 10 volts. There's an important pin here called SB and BTC. So that pin is how you tell the chip if you want straight binary or binary 2's complement. And the way you do that is the bar means that you're tying that pin to ground. So that means it would be active low with the bar on there. So if I were to tie pin 8 to ground, that would mean I want binary 2 complement. And if I tied pin 8, on the other hand, to my power, so that'd be straight binary. So you actually pin strap pin 8 to tell the chip how you want the data. So if we wanted to connect up in a bipolar way, we would want to put plus or minus 10 volts from some sensor, and we'd want to connect to VN, and there would be a network of resistors and capacitors connected to the chip in this way. So for bipolar, we would want to use binary 2's complement. So we would put the pin, the BTC, tied low, and we would want binary's 2 complement, so that minus 10 volts would be 8000 hex. That's what we would want. And then 0 volts would be all zeros. And then as you get towards plus 10 volts, very close to plus 10 volts, you would have 7 Fox, Fox, Fox. So that would be the range of minus 10 to almost plus 10. And each least significant bit would be 305 microvolts to give us that range. So that's how bipolar would do. Bipolar, you would want to use binary 2 complement or signed 16-bit. If it's unipolar, a unipolar type of sensor that you're connecting to, you'd want to go 0 to 10 volts, for example. And the input voltage there would be connected here, and then that's what the network would look like. Okay, so that would be unipolar. And then for unipolar, you would want to take the straight binary and tie that high so that you're running on straight binary or unsigned, so that all the way, where is it? 0 to 10 volts is here, so 0 volts would be all zeros. The mid scale would be 5 volts, and that's going to be 8000 hex or 8000 hex, just one least significant digit below that, least significant bit below that would be 7 Fox Fox Fox, just right below 5 volts. And your resolution here would be 153 microvolts. And then all the way at the top end, you're almost right at 10 volts, and that's going to be all Foxes. So that's what it would look like. This particular analog to digital converter gives you both capabilities, and it's up to you how you connect it and how you use it.
Here is a servo motor. You see the motor shaft here quite clearly, and it's actually what's called a double shaft motor, and on the other end of the motor we put a motor encoder. And the motor encoder is a US digital motor encoder. It's a 2000 line motor encoder, and you can actually see the pin out. You can see the pins off the encoder. You have ground, you have the index, you have the A channel, 5 volts, and then you have the B channel. So I'm going to pull the cover off, let you take a peek here at what's below. So there's actually, you can see the Mylar encoder wheel. It's clear and it has some lines on it, and you can actually see the index channel as well, but the outer perimeter there is a sequence of lines that are read by the motor encoder head. Here it's got A and B as well as the index light sensors built in there in the reading head.
In order to read the motor encoder, you need something to count the pulses, and this is an example, a 32-bit quadrature counter with serial interface. So it's a 14-pin chip, and you connect the A channel and the B channel to the chip here. Of course, you give power, and then you can communicate with Arduino or whatever over here doing a serial interface. There's also an index connection. If you remember that code wheel that I showed you, you've got lines on the code wheel, and when you shine a light through that and you have a sensor, a light sensor on the other side, and then you turn the code wheel, you're going to get alternating pulses on each the A and the B channel. And when the A channel leads the B channel, that's going in a positive direction. On the other hand, when the B channel, the rising edge of the B channel leads the rising edge of the A channel, that's going in a negative direction. And that's how the counter works, is based on the phasing of the A and the B. And what you do is you basically count the rising and falling edges of A and B. So they call that quadrature. And the transitions of the counter, it changes on the rising edge of an internal clock. So here you're changing from a Fox Charlie, say a -4. You're going up to a -3 because A is leading B as it was clocked there. And then here you're changing from -3 to -2 because you've sensed the B. And then here the A drops, so you're going from -2 to -1, and then the B drops, so you're going from -1 to 0, and you keep going. On the rising edge here, you're sensing that the A has risen again, so you keep going, and then here you've got the B going up, so you get to see the 2. Now what happens is B drops. So this dropping of B is actually going to be change of direction, and that's shown up from going from 2 to 1. So we're going down now. And then A drops, so you're going from 1 to 0. And then B rises again, so you're going from 0 to -1. And then A rises, so you're going from -1 to -2, and so forth. This notion of quadrature says that you're counting both the rising and falling edges of A and B. So if in my example I had 2,000 lines, so that means that I would get actually 8,000 counts per revolution of that motor I showed you. And you get the data into your microcontroller, and the data looks like 32-bit data. They're only showing, I think, 6 nibbles here, but you get signed 32-bit data directly into your controller, indicative of the position of the motor. So in summary, in the signed versus unsigned, we looked at how the data is represented, binary, hex, and decimal for both signed and unsigned. We looked at bitwise operations. That was very important. Then we took some examples. We looked at the Velodyne range to target. For the Velodyne, that's the LiDAR, the laser rangefinder, and that looked like an unsigned example. Then we looked at unipolar sensors connected to an Arduino and thought about that. So that was also unsigned. And then we looked at an analog to digital converter that could go either way. It's a Texas Instruments 7809. So that could be unipolar, configured for unipolar, or it could be configured for bipolar. Unipolar is unsigned, bipolar is signed. And then the last thing we looked at was a terrific example of a signed 32-bit integer coming from a motor encoder. Hope you enjoyed it.